We have a panel today taken from staff across the School of Physics, and I'm going to start by introducing them. So we have Dr. Hannah Wakeford, who's an astrophysicist and lecturer in environmental physics. We have Dr. Jon Fellows, who's a theoretical physicist and a lecturer in environmental physics. We have Dr. Tomas Martin, who's a materials physicist and lecturer in nuclear science and engineering. We have a good friend of the school, Dr. Tom Hull, who comes from the Centre for Environmental Fisheries and Aquaculture Science and Centre for Ocean and Atmospheric Sciences at the University of East Anglia. So just a couple of notes before we get started. We hope that you will ask us questions. So there is a Q&A section in Zoom just at the bottom of your screen, and feel free to put your questions in there as the discussion progresses. We're going to start with a few short presentations given by some of our panel members. So I'm going to invite Hannah to give her presentation, the first one.
Now, can everybody see Forky? Forky's here to ask a question that we really need to answer before we can start talking about anything else. And that is really quite simply, what is climate? If you haven't seen Forky ask the question and you have Disney Plus, I really encourage you to watch them all. So when we think of climate, actually what most people think of is weather. Weather is actually the more localized and time-specific aspect of our climate. So weather happens absolutely everywhere, but it's not the same everywhere. It is very, very different. And you know, we can have a beautiful day here in Bristol, but it can be snowing or raining somewhere else. But the climate is really this global system. It's the average of that weather over a much, much larger area. So, and how that changes over seasons and years rather than over hours and minutes. So the climate is this global set of patterns that we can monitor and see how different things affect it. And that is very, very different from that more chaotic and localized weather systems. So when we're talking about climate change, when we're talking about anything to do with how our environment, our planet is reacting, we're really talking about the global climate and how something local might be very, very different to what is an average over what we're seeing. And we'll be talking about lots of different aspects of that today. We've got a couple of presentations showing you some of the local effects of a global climate and what actually happens and how those link together. So Earth's climate really involves absolutely everything that you can think of. So think of something and it will have an impact on the global environment. So here I'm just listing a few of them, just showing off my keynote skills here. It's the oceans, the ice. The amount of ice is really important for monitoring and balancing our climate. The sun's energy, how much energy the sun is outputting. Over time, actually, over the 4.5 billion years of our planet, the sun has changed its energy output. And that affected our climate quite dramatically in the past. So the sun has a huge impact on the Earth's climate. And if you look at other planets, I'm a planetary scientist, I study exoplanets. If you look at other planets, you can see how the influence of the energy from the sun can change the way that a climate of that planet reacts to it. Our atmosphere is, of course, one of the most important things that is associated with our climate. But the atmosphere is reacting to what the oceans are doing, what the soil is doing, what biology, biodiversity, the land, vegetation is absorbing and giving out. So it's all in balance around the things that we are doing. And cities, as we've seen, have a huge impact. Industrialization across the planet has had a massive impact on our climate, and that's really the focus of what a lot of us do, is trying to understand how climate is being changed by human action. And since the beginning of our planet, volcanoes, of course, are giving out different gases and reacting and giving out different things that can change our climate. So it's all a big balancing act between a huge number of things. So these complex systems have to come together and work together to try and understand what will happen over this global scale. And the biggest one that I'm sure all of you have heard of is this increasing global temperature. And this is been monitored and shown to have increased dramatically since the Industrial Revolution, the output of huge amounts of CO2. Now, CO2 is what is called a greenhouse gas. It basically allows the planet to keep in more of its heat than other gases. And water is also a greenhouse gas, but it reacts in a slightly different way. And the increase in CO2 that we've seen since industrialization has really caused dramatic change in our planet. What you're seeing on this figure is the difference between the 1951 to 1980 average temperature and the 2011 to 2020 average temperature. Now, you might think those are arbitrary, but what I want to show you on the next figure, you can see, look how much hotter it is. The next figure here is showing you we're comparing this range here to this range over here. So from around the 1950s to the 1980s, there's blue, there's red in there. So there's some hot years, there's some cool years in the UK. But in the 2011 to 2020, they're just really hot years. But what I want to point out to a lot of people is that this average that we're comparing it to in that previous figure is not even as cold as it used to be. So we're talking about industrialization in the late 1800s to the early 1900s, and the changes that have occurred since then. The baseline that you see, where we're saying the planet is heated up by 3 to 4 degrees, is compared to a time when it was already heated as well. So this is a really big change that's happened to our planet because of what we are doing, what we are putting out in the atmosphere. One of the fun things that I get to think about as a planetary scientist is the different effects that the atmosphere can have and the way that different things on a planet can change what is measured. And one of my favorite things to talk about is something called rain shadows. So I just wanted to highlight how the physics that we know and the atmospheric dynamics really can drive what the climate and the weather is like. So one of these things called a rain shadow is when there's wet air, so it's moist air that's kind of come off an ocean. It hits a topographic feature. So this is a mountain. So we're coming off the ocean. We've got wind driving. It hits a mountain. It's forced up that mountain. As it's forced up that mountain, it forms clouds. It condenses and rains out. So that's what we're seeing up here, that it is now raining down, removing that moisture from the air. Now, the act of condensation itself, the act of forming water droplets from that gas, actually releases heat into the air. It releases the latent heat, and that heats up the air at the top of the mountain. Now, the wind is still driving it down the other side of that mountain, and as it's driving it down, it's actually heating it up even further because it's then being compressed as it gets pushed down towards the ground. So we've got really warm air coming down from the other side of this mountain, because not only has it been heated by the fact that it's already condensed and rained on the other side, but it's being heated because it's being compressed. And this causes very dry, desert-like areas on the other side of an incredibly wet rainforest-like mountain. And this actually, you can see it around the entire world. Some of my favorite ones are, you can see in the Hawaiian Islands, form a perfect diagonal rain shadow from the North Ocean to the South Ocean. You've got the rainforests in the north and the deserts in the south. And these rain shadows actually can cause the moisture to be taken out of that air. And we've seen it in the past, and especially last year, the increase in wildfires, because you've got very, very dry, very, very hot regions. So one of the things that's trying to understand about climate change is if we increase the temperature, we increase the effect of these rain shadows. We increase the amount of precipitation that we expect to see on the leeward side, on the windward side of the mountain, and we increase the dryness. And we can see, this is just looking at last year, all of the wildfires that happened across the planet. Now, not all of these are caused by that rain shadow effect, but a lot of them do have those aspects associated with them. And I wanted to show this on scale. So I put on scale, this is the monitoring of the United States wildfires for 2020. You can see just how dense those dots are along the coast in California. Look at that density on the global map compared to other regions of the world. Use this as a scale to see, holy crap, South America is in trouble. South of Africa is in trouble. And Australia, we saw last January and February was just on fire. So there's just a huge amount that is going on in our climate right now, which has massive feedback effects. So this is the doom and gloom starting point for our panel today. And I just want to outline some of the side effects of increasing the CO2 concentration in the Earth's atmosphere. And we'll go into a little detail about some of the others. So oceans, they get warmer, so they reduce the amount of phytoplankton. So you reduce the amount of the smallest animals, the largest block of our food chain gets reduced, and that has an impact all the way up the food chain. The increase in the CO2 is actually what's causing the bleaching of the coral reefs as well. So it creates carboxylic acid in the oceans, and that really has an effect on our coral reefs and then the diversity of the marine life. So most of the marine life that we see is in the top 5 meters of the ocean, and that is being destroyed by this increased uptake of CO2. The atmosphere is being heated. There's tons of things that has an effect on: melting of the ice caps, reducing the permafrost. Permafrost actually contains, the land itself contains a huge amount of carbon, and that's holding it in. And there's just a huge amount that is kind of scary. But I wanted to end my tiny section that I've gone on too long for on some things that we can do. And these are things we've learned since primary school: reduce, reuse, and recycle. Those things do actually have an effect, and they really can help. So there's a number of things here, and we'll be posting these resources afterwards as well, that we're going to be talking about today that we want to make sure that we are doing on a local and a global scale. So I'm going to stop there.
Thank you very much, Hannah. That was great. Our next speaker is Tom.
Okay. Let's get that sharing. What can people see? Mine. Great. Okay. Okay, so I'm going to highlight some of the work researchers are doing globally to kind of reduce some of those uncertainties that Hannah's previously mentioned there. So it's mostly an excuse to demonstrate Boatface, one of the autonomous vehicles that I work with. On the other side, we've got some of the gliders, which are probably the ones I work with mostly. So let's get into it. I mostly look at oxygen and how oxygen feeds into the global carbon cycling. As Hannah pointed out, phytoplankton are very, very important for how oxygen is produced. You know, a single species of phytoplankton is estimated to produce 20% of all the oxygen. I think it's pretty obvious to most people that oxygen's quite important. It's biologically important. It's important to many things, but what people might not realize is that it's intrinsically linked to carbon cycling, and through photosynthesis, for each mole of carbon which is taken up, there's a similar mole of oxygen being produced with a fixed stoichiometric relationship between those two. This is really useful because measuring CO2 in the ocean is really kind of difficult directly, as Hannah mentioned again. There's the carbonate chemistry of CO2 means that one, while we think there's a lot of it in the atmosphere, it's still a relatively small fraction of anything we're trying to measure. And coupled with that, it turns into carbolic acid, and that carbolic acid reacts with all sorts of other things, and generally very, very hard. It's particularly hard to measure it automatically with some sort of remote system, whether it's by satellite or some sort of drone you've used. And you might have noticed the oceans are really big, and so going out there with a ship trying to measure the whole thing is incredibly challenging. So you can measure oxygen instead, and that's much easier. But given that, there's still really large uncertainties about what these oxygen fluxes in and out of the atmosphere and between various water bodies are doing. So people are out there trying to measure it. Oxygen itself has seen a global decline over the last 50 years. 2 to 3%, depending on how it's measuring things. But the main effect of that is, while global oceans have warmed up, they've reduced the solubility of oxygen, reduced the ability for the oceans to hold on to their oxygen. We've also seen the expansion of low oxygen areas. So these are areas where the oxygen is so low that it's starting to impact the biology, you know, fish are dying, that kind of thing, or it's affecting how nutrients within the seawater are being cycled. And predicting where these are going to happen, how they're going to expand, and how they might change in the future is really difficult. And so we'll get into that next. What's causing it? As I mentioned before, there's these solubility changes, so you know, inversely proportional to temperature. As temperatures rise, oxygen solubility goes down, but there's more circular interesting responses to that as well. So one of the other things that warming temperatures are having, effects warming temperatures are having on the sea, is the sea stratifies stronger and for longer. So this is the surface layer of the oceans becomes more buoyant because it's warmed up, and that acts as a barrier to the water below. And so you end up having these large regions of the ocean which are isolated from the atmosphere, so they don't get ventilated. Any oxygen that's down there is what oxygen stays down there. And so anything living down there is going to consume it, and it's not going to get replenished. And so what we're seeing here is a sort of some modelled output from the North Sea that shows that sort of the northern North Sea stratifies in summer. And this is normal. This has happened as far back as we have measurements. But what's happening is it's stratifying for longer. So those bits below are staying isolated for longer. And it's also stratifying harder. And so the actual small amount of diffusive oxygen that does move across those water layers isn't happening as much. Coupled with that, we've changed how we put nutrients into the ocean. So this is runoff from farming activities, but most of the models are also predicting, with changes to global ocean circulation, the amount of nutrients that are brought in from the deep ocean is going to change, we think. So why do we care? So the shelf seas are really disproportionately important to the global carbon cycling, even though they're like 10% of the global ocean could be considered shelf. So this is the waters which are less than 200 meters deep. The seasonal cycle, with the massive amounts of primary productivity, the massive amount of plant growth we get in those oceans, partly coupled by because they connect near to the land, drives these really big fluxes of carbon. And if you extrapolate from what our best guess of what's happening in the North Sea, it looks like 20% of the CO2 that mankind has ever produced has already been taken up and sequestered by this shelf sea pumping action, where each year that sinking phytoplankton matter actually gets kind of pushed and dumped into the deep Atlantic. So important process to kind of capture and understand how and why. So the way I do it is we measure oxygen. We then, using physics, predict what the concentration of oxygen is going to be in the future through air-sea gas exchange, bubbles being injected, water masses mixing together. We look at that predicted concentration and compare it with a subsequent measurement. And the difference is biology. So if it's positive, we've taken carbon out of the atmosphere, and if it's negative, we haven't. We've released it. And how? The way I do it is with these things called gliders. So this is a robot. It can change its buoyancy to allow itself to swim through the water. It has various sensors on it. And the advantage of this is, without having to burn a load of fuel to go and send a boat out to go and measure the fact that we're burning too much fuel, we've got a autonomous vehicle that can go out there and monitor for long periods of time, and we can start to tease apart the kind of natural interannual variability. You know, this year is a hot year, this is a cold year, and try and figure out what these trends are over time with vehicles like this. And that's kind of me. So yeah, we can use oxygen to measure carbon. We need a lot more measurements to figure out exactly what's going to go on, and robots are a great way of doing this. Thank you.
That's great. Thanks so much, Tom. Okay, so we're moving on to our third presentation, and that's Jon Fellows. Jon, do you want to share your presentation?
Yes. Have I successfully done it? Great. So Usually I'm the bleak one, so I'm really now feeling bad about following two bleak talks. So one thing Tom's been talking about is how we measure what's happening with the climate. Now I want to convince you that there's also some theoretical grounding for really understanding what we're seeing. And this is inspired by news from last week when it was snowing in Texas. And you always get, when things like that happen, people coming on the television and saying, oh, I thought it was global warming. So I just want to convince you right now that to a theoretical physicist, it snowing in Texas is an indication of global warming, despite snow itself being cold. And the culprit, the thing I'm going to blame this on, is the polar vortex. So what the polar vortex is a large mass of cold, low-pressure air that's sitting above the North Pole. There's also one on the South Pole, but I'm going to talk about the one on the North Pole, which exists simply because the North Pole is getting much less sunlight than everywhere else. So you get lower temperature and lower pressure because of less heat injection. Now, on the edges of this mass of cold air is where we find the jet stream, which you will have heard of, or if you've ever flown back from America, you'll have been there. It's the very fast-moving band of air that's going around these high-latitude areas. And this is a picture I took last night, just screen grabbed some satellite imagery of the polar vortex. And if we look closely at this, the thing I want you to notice is that those edges are not smooth. So we're looking downwards on the North Pole. The blue and purple is a temperature map of the cold area. In the picture I showed before, there was a quite smooth transition from the cold to warm. This isn't what it was looking like recently. So in a standard picture of what we'd call a strong polar vortex, what you've got is the cold air mass is completely contained above the North Pole, and it's got these nice smooth edges. But what can happen along the jet stream along the edge is it can wiggle. Now, as it's wiggling, these oscillations are essentially pulling a cold air mass down southerly towards the places where you and I live. And it carries along the weather front where you've got hot meeting cold, that's where condensation and snow happens. And then behind that front, you've just got cold air. Now, I said I'd go from a theoretical physics perspective, so I'll start using a word here. This wave motion, that's a wave on a rotating fluid, the Earth is rotating and the air is a fluid, is something that we'd call a Rossby wave. I'll carry on with the cartoon version for a second, though. So now I've got these waves forming on the edge of the polar vortex within the jet stream. And now I'm going to imagine we've got a situation like we've currently got, where these edges are not so well defined, a weak edge. You can imagine a scenario now where you've got an extreme dip within this wave, and the edges start touching each other, and a trough within that wave can get pinched off. Then what I've got is a free-floating mass of cold air, or a cyclone, that's just going to move about on its own and bring extreme weather conditions. Now, the question you're all asking yourself is, what does this have to do with climate change? John was supposed to talk about climate change. I think we need to do some maths to see why I bring this up. So I'm going to do the standard theoretical physicist thing of take out a piece of paper and write down all of the things I know. Now, I don't know many things. One of the things I know is that angular momentum is conserved. The angular momentum of the air is going to be its own internal vorticity, and then the rate of rotation of the Earth itself. And the other thing I know is that the air is a fluid, and fluids don't like to be squished. So I write down equations that say those two things. Then I combine those equations into a single governing equation for the system. And because I'm looking at a wave along the edge of the jet stream, I'll look for a wave solution and then write down the dispersion relation based on the governing equation. This is what I call a Rossby wave. You can Google Rossby waves if you want to go through this working yourself. I encourage everyone to do their own working when it comes to climate change questions. Now, the next thing any theoretical physicists do when they've got an answer is work out what that answer is telling you. So I'm going to analyze the dispersion relation between the frequency of my waves and their wavelength. Now, if I had very fast moving background flow and a small, this beta parameter is essentially how close are you to the North Pole, so it's 0 on the pole, it gets bigger as I move away. When it's very fast moving, I've almost got a linear dispersion relation. And the thing we know about linear dispersion relations is, well, you recognize them. That's the kind of thing you see for light or for sound. So that is a frequency that's proportional to a wavelength. If I have a slow background flow, the wave becomes dispersive. And dispersive waves tend to break up. So here is where I'm drawing the link between that weak jet stream with those ragged edges and that strong jet stream with the smooth edges. So the difference being a tendency to break up and a tendency to hold together. There's a bit more physics information we need here, which is simply that the main flow that's driving the jet stream is what we call a thermal wind. Now, a thermal wind, I could do my theoretical physics thing again, just get down a piece of paper and write down all the things I know. And one of the things I know is the ideal gas law. And I don't know, just Google thermal wind and run through the working yourself. You can show that the wind speed is proportional to a temperature gradient. So I'm going to just put together the two pieces of things I know. One, to have a strong and stable polar vortex, you need a fast thermal wind driving that jet stream, which in turn needs a steep temperature gradient. And the other thing I know is that if the jet stream gets slowed down, these waves upon it become dispersive. And I want you to imagine this meaning it gets wobblier or more ragged. And that's when you see those extreme weather events. The new piece of information I'll add is that global warming is a uniform process. So heating from the sunlight is hitting different parts of the Earth at different angles, some more oblique than others. And that's why you get a hot equator and a cold pole. Whereas the greenhouse effect, which is CO2 absorbing and re-emitting radiation, is uniform. So the process of global warming softens north-south temperature gradients, which means, I'll follow my chain of logic, the jet stream gets slowed, the Rossby waves become dispersive, extreme weather happens. So next time someone says, why would global warming make it snow in Texas? Just tell them everything I've just said.
Thank you very much, Jon. I think we've learned so far that physics is very good at describing all of the problems of climate change and how climate change is progressing. So Tomas, can you give us some hope? Can you tell us something about solutions?
Yes, I can do my best. Let me just share my screen. So I'm a material physicist these days, and a lot of the work that I do is looking at things really, really close up to try and improve them. So that might be a solar panel, it might be a fission reactor, it might be a future fusion reactor. But in the past, I worked in the renewable energy industry and consulted on a very large number of plants around the world. And so for today, I'm going to zoom right out and give you a big picture of where we are when it comes to electricity in particular in solving this problem. And so this picture, which is also my background, is actually Cougar Wind Farm in South Africa, which I consulted on back about 10 years ago. So it's, you know, the main thing we're talking about here is how do all of these different contributions add up? And when we talk about climate, there's kind of two main things we have to think about. The first is what are our emissions? What are we as a world producing in terms of the gases? And it's about 51 megatons or gigatons even of carbon equivalents. And so that's methane, it's carbon dioxide, it's various other things. And when we talk about it, we have to avoid, I'm just going to move this out of the way. We have to avoid a rise of more than 1.5 degrees C to get to where we want to go. Now, that's a very, very difficult task to get to, even by 2050. Recently, President Biden has taken over in the US and said that they want to get to 0% electricity, zero carbon electricity by 2035. The biggest thing we need to do is, or the easiest thing to address with this, is looking at our electricity sector. And if you look at the breakdown of our carbon emissions, the electrical is somewhere just under a third of that. But actually, a lot of this manufacturing piece of the pie and the transport piece of the pie, we can also convert to electric power. And so solving the electricity question is really important, firstly, because we can remove this big chunk of our emissions, but also potentially a lot of this stuff can be changed from fossil fuels to electric. And we'll talk a bit more about that at the end. Our electricity mix, on the other hand, isn't great. So if we look at the mix of all of the world's electricity supply in this year, we've got something on the order of 64% of that comes from fossil fuels. And really, to get rid of this problem, we need to reduce this as much as possible. And in particular, coal is a much, much dirtier emitter than anything else. So we want to try and get rid of that as quickly as we can. And one of the issues with this whole question, which doesn't get talked about enough, is that there is a big lag between someone inventing something and it actually getting to the scale that we need to address a problem of this nature. And so if we look at different inventions over time, it might be on the order of decades before we actually see huge numbers of it. So my grandfather worked for Lloyd's Bank, and I remember when I was a kid, him telling me about the first computer going into the headquarters of Lloyd's Bank in London in the 1950s, and it was the size of a room, right? And it wasn't until the mid-90s that we started seeing computers in people's houses, and now everybody's got them, and we've got them in our pockets. And that's one of the things that we have to face with this problem, is that if we invent some magical technology today, it's probably 30 to 40 years away from actually contributing in large numbers to this problem. Now, helpfully, 30 years ago, we were already underway with this process. And so one of the hopeful things that I'll talk about is just how dramatically the energy networks have changed over the last 10 to 15 years. And so if you look back in sort of the 80s to the early 2000s, what you'll see is this process is underway. So the number of patents in solar and wind technologies in particular were outpacing how much wind and solar we actually had on the grid. But around about 2007, the amount of installations started spiking. And I can remember during my PhD, and I started in 2008, the price of a solar panel was about £6 per watt, which made it really just a thing that you would do because it was the right thing to do for the climate, but it wasn't really a cost-effective thing to do for your house. Over the next 3 years, for a number of reasons, the price plummeted. And so we've seen this Moore's law, like with computer chips, where computer chips get faster as time goes by. Solar panels have got dramatically cheaper, and we're now below that relationship. And so now solar power is the cheapest energy that we have. And the world hasn't really caught up with that idea yet. And so the new paradigm that we find ourselves in is that renewables are very, very cheap. And so this is something called the levelized cost of electricity, which I won't go into how that's worked out. But essentially, these bars show the lowest price and the highest price equivalent cost of electricity, including all the factors. And what you'll see is that, if you put solar on your roof, it's not very cost effective. But if we compare large-scale solar photovoltaic plants and wind farms to existing conventional things like coal and gas, they are dramatically cheaper now. And so this is something that wasn't true even 10 years ago. And so it's very much affecting the way that we decide to make our investments. And what's particularly significant in the last couple of years is these diamonds. So these diamonds are existing plants that we've already built, nuclear, coal and gas. And the diamonds indicate the cost of generating a megawatt hour of electricity for the ones we've already built, so keeping them going. And what's interesting is that if you look at wind and utility scale solar, they're below that price for some places. If you've got the right amount of sun, the right amount of wind, it's actually more cost effective to build a new renewable farm than it is to keep your coal plant going. There's a caveat to that, which is obviously that nuclear is clean, and the cost to keeping the existing plants running is very low. And so we want to keep those going as long as possible. And there's a lot of work going into extending the life of our current plants. But this is a really promising development and something that we really want to keep looking at. And so the sort of main message of my talk is that we're getting somewhere. Carbon emissions have started to plateau. In 2016, they went down despite the fact there wasn't a recession, which was the first time that had ever happened. In general, carbon emissions tend to go up as the economy goes up. Now, this year, they've gone down by about 7%. But what's surprising about that is that with everybody working from home, with the pandemic and so on, you would have expected potentially for that drop to be lower. And so the fact that we've had such disruption to our system and only had such a small drop is a sign that we can't solve this by individual choices alone. This is something where we have to address the systematic grid of our energy production. But things are changing in the right direction as a result of this change in pricing. And so both China and India are dramatically reducing how much coal they're planning to install. And just in the last year, the projections of how much future coal power stations India is going to build have fallen by 86% compared to what we predicted last year. And renewable capacity is predicted to overtake gas and coal across the globe by 2024, which is not very far away. And as I said earlier on, solar PV is now the cheapest form of electricity that we have at large scale. So we are making progress, and the tools that we developed earlier are now actually making a difference to this problem. So there's still a lot of open questions, and there's far too many things to talk about for such a short talk. But we have new technologies, and so we've got things like marine power, tidal and wave. New types of nuclear power are very promising, particularly things like molten salt reactors that allow us to transmute our own waste, and fusion, which is, we're approaching the point where ITER is going to start potentially generating more power than we put in. But these are all quite far away. Another very interesting one, which hasn't got as much attention in recent years, is geothermal. And there's a lot of investment in new types of geothermal plants that look very, very promising. But there are still some questions that we have to face as well to solving the problem. So the first is how do we price carbon risk? So we've already got some projects which are cheaper than fossil fuel, but we're not paying the cost of those fossil fuel plants to the planet. And so pricing that is going to be something that's very important to keep this incentive going. The second problem is that all of these different types of power last for a different number of years. And so a lot of the things that might be quite helpful, for instance, building a Severn barrage, which would produce around 10% of the UK's power, but lasts 120 years, the banks don't know how to finance that because they want a return on their investment within 25 years. And we're not really set up as an economy to deal with those longer term investments. And then there's some more sort of worrying potential problems that we might get to further down the line, such as our availability of lithium, cobalt, neodymium, these precious metals, which a lot of renewable technologies and energy storage rely on. We potentially are going to run out of those before we get to 100% carbon. And so that is going to be increasingly something we need to think about. Equally, if we do transfer to electric cars and trucks and trains instead of fossil fuels, well, that's going to dramatically increase how much electricity we need to generate. And so it's not just about replacing what we currently have. It's probably we're going to be 3 or 4 times the amount of electricity we currently produce. And then lastly, one of the big challenges of renewables in countries like the UK is that they require a lot of land. The energy density of solar and wind is very low. You know, a wind turbine has to be put about 10 widths of the blade apart from the next one to avoid them interacting with each other. And so when we're a small country that doesn't have a lot of land, and most of that land it's not possible to give permits for installing that stuff, it's really difficult to see how we're going to be able to fit that stuff on there. And so that's one of the ways that we need to think about all the different technologies. And Jon talked a little bit about this idea of in Texas, and I know I'm going really, really long, but I just want to talk about this example from an electricity grid because it's really, really interesting. And one of the biggest problems we're going to have in the future is balancing our electricity grid. And this example in Texas, where we had this deep freeze over about 10 days ago, is a really interesting problem. And for about 4 or 5 days, most of the people in Texas didn't have any power. And the reason for that is actually because it was so unexpectedly cold in a place that's not normally cold, the gas wells froze and they weren't able to supply natural gas to the gas power stations. And the grid is a constant battle between the amount of energy we're producing and the amount of energy we're using. And wind and solar are variable, so we need to have enough flexibility in the system to account for a day where we don't have enough sun or a day that we don't have enough wind. In Texas, that wasn't the problem. The problem was that everything froze. But that's something we expect to happen more and more with climate change. And so we have to think about the best ways that we can do this. And the Texas electricity grid was not connected to anywhere else. And so unlike we're connected to France and Norway and the Netherlands, we can import electricity when we need to, and we do very frequently. But if you don't have that grid that allows you to do that, you can get into serious problems. And so just to finish off, I just wanted to show you very briefly what we're currently generating to get a scale of the problem. So this was taken during Jon's talk. So it was about 10 minutes ago. We were generating about 17% of our electricity from solar today, and about 9% from wind. But we still got this huge amount of gas. And so that's the next big challenge for the UK. But I think the main message here is that this is a huge challenge. We have a lot of tools that we've developed, but we need to use all of them if we're actually going to solve this problem. And I will stop at that point, having dramatically overrun like everyone else.
Okay, thank you very much to our panelists for their wonderful presentation. So I think we learned a few things. We learned that physics is excellent at describing how climate change is occurring and how it impacts our weather. We have learned that physics can be used in terms of thinking about how we provide energy in the future. And we've learned that physicists can't stick to time. So we're a little bit further over on our time than we intended, but we have some excellent questions. So if you have any questions in the Q&A section at the bottom of Zoom, put them in there. And if you like somebody else's question, there's a little thumbs up symbol, and please click on that so we know which questions you'd like to have answered first. So Jon is also going to help me with posing the questions to the panel. So we will start with the top ranked question currently. So this is for all panelists. What do you consider the most impactful careers for young physics graduates? What are the most impactful careers a young physics graduate should be considering if they're concerned about climate and environmental issues? This is for all panelists. Who wants to go first?
I mean, maybe I'll go first, having done a couple of those different tasks already. I mean, I think there's a lot of work at the moment in going into building these things. So working on big offshore wind farms is a big player at the moment. We've got big construction projects like Hinkley Point C, the electrification of the high-speed rail. You know, there's a lot of good routes for people with a physics background to go into those kind of careers. The other thing is obviously research. There's huge amounts of things we can do in terms of understanding how these things behave better, designing new technologies. And I think as well, a lot of this is about how we put these things into practice and policy. And so having technically minded people go into consultancies, to think tanks and so on, so that we can have a constructive conversation about the numbers is really, really important.
Yeah, I think Tomas kind of covered all of the different aspects there. Myself, as a planetary scientist and more of an astrophysicist, I would say the main thing that I would be looking to is we have the best Met Office in the world. The UK Met Office is just so much better at our climate models than anywhere else, and you can really apply yourself to a huge number of problems and different ways of looking at the data and understanding that. We demonstrated at the beginning that we're all about trying to understand and pick apart what is causing it and how it's doing it. So that is something that's really useful to understand through time, and that's one thing that that's where I think some applications can be really helpful in understanding these 30-year timescales.
Does anybody else want to come in on that? Okay, maybe we'll move on to the next question then. So, what's the best, most promising way for us to store renewable electricity on such a large scale? So intermittency is always an issue with a lot of renewables. So how do we address that without necessarily having to use batteries, which can cause their own problems?
One of the most interesting ones is actually running hydroelectric power in reverse. So if we've got too much power, we can put the pumps in the opposite direction and pump the water back uphill. And a lot of hydroelectric dams do this a little bit already, but there's a lot of talk about installing these more on hills that don't necessarily have a river, so that we can have this kind of storage through gravitational potential energy. Another good one is thermal storage. So some power stations now are starting to get these thermal bricks, where they essentially use the excess heat to store energy in the bricks, and then you can take those to houses in India, for instance, which would normally be burning coal, and these bricks can be their source of heat for the day. And so there's some interesting ones there.
So many of the technologies that we've spoken about are things that already exist and are already well developed. Are there things that are, you talked about this 30-year timescale in terms of developing new technologies. Are there things that are still in the lab now that potentially could be contributing in 30 years' time?
I don't want to be the only one answering questions, but I
think
to
everybody. Anybody can contribute.
Advanced nuclear solutions are really interesting. So, one of the issues which we have with current fission is obviously storing the waste. And so the next big sort of development is these fast reactors, molten salt reactors, liquid metal cooled reactors, where we don't slow the neutrons down like we do in a water cooled reactor. And the idea is there you could put a lot of the problematic waste in the reactor after you've used it and transmute it into things which have a shorter half-life, and so you don't need to worry about storing them for long times. So the ecosystem around that is really interesting. Fusion obviously is very exciting. A lot of people really get into it, and I think we are making a lot of progress in a way that we perhaps haven't been. We're actually getting to the point where you could imagine a power reactor for that, which is quite exciting.
Okay, thanks very
much. I've got a question from the emails that will get Hannah talking. There's an ozone hole over Antarctica. Why isn't it above the big polluting areas?
Yeah, I really like that question because it's non-intuitive, right? There's no CFCs that were being emitted over Antarctica. So why is the ozone hole over Antarctica? Majority of CFCs, which these chlorofluorohydrocarbons, which break down ozone and cause this hole in our ozone layer, come from Europe, Russia, Japan, North America. Why are they getting to Antarctica? And the reason is the ozone actually lies in a region of our atmosphere called the stratosphere. And that's much, much higher up. So it's about 50 kilometers up. And the CFCs have to get to that part of the atmosphere to break down the ozone. And the very, very cold air over the massive landmass of the Antarctic, compared to even just the Arctic, there's no landmass there. So it's not as cold in the Arctic as in Antarctica. And that really cold region actually allows this material to go up into the stratosphere, where it can then be activated by the UV light such that it destroys the ozone layer through the generation of chlorine radicals. So it's the fact that you've got this very cold region which allows this material to go up to the part of the atmosphere where it can cause these chemical reactions to happen that mean that that hole is very much concentrated there. And then in a similar way to what Jon was talking about in terms of that polar vortex, there's one in the south as well, but it's much more confined due to the fact that it's a landmass that it's on. So the confinement of that polar vortex also means that it kind of keeps that material there. It keeps it swirling in that polar cell. So once you've started generating that, after these chlorine radicals go off and destroy ozone, they hang around for 2 years up there and they stay in that polar vortex. So you're building up material there and you're keeping it there. So the ozone hole really expanded over the Antarctic due to the fact that we've got much colder region. We've got the ability to push that material further up into the stratosphere, and you can keep it there for a really long time.
I think just to add, Hannah, I think it's a really great example of when we actually can, when we do something about a problem. It's estimated to be healed back to where it was by 2080. So legislation to ban a problem works.
Yeah, and it's really about noticing these things and pointing them out. So it's took 11 years before any legislation came in to stop that from happening. So the more we measure things, and we've got an amazing array of satellites measuring our planet and trying to understand these things, the more we can understand these things and know what's happening now, the more we can prevent bad things from happening in the future.
And that was discovered by 2 chemists and a physicist. Well, initially by a physicist and then later explained by 2 chemists. So maybe going back to what careers can help.
Talking to people helps. Talking to other people.
Yeah, weighing in. I mean, obviously biased as a marine scientist. There's very few problems we have nowadays in marine science which don't involve physicists and chemists and biologists all working incredibly close together, because they're all so incredibly linked. Just as an example, one of the problems we're working on at the moment to improve said Met Office models is the effect that the models are underestimating surface warming because they weren't coping for the fact that the phytoplankton themselves are absorbent. And so tweaks to the algorithms are like that. So there's tons of opportunities for these kind of things.
And I think also with the ozone layer, the interesting thing is that the same people who were trying to stop the legislation about the ozone layer are the same people that have been trying to delay action on climate change, who are also the same people that were trying to delay action on smoking. There's a cottage industry to this kind of like trying to stop the companies that will pay these people to delay things. And that's a really interesting change in the last few years. Is we've gone from how can we pretend that this isn't real and not happening to how can we delay it, and I think that's something that we need to recognize, that there's a lot of people who would prefer not to take action because there's a financial imposition for them as a company, and that's a big part of the discussion.
So maybe that brings us to one of the other questions that we have in our Q&A. So do you think there will be significant changes to human lifestyle and society due to climate change? So this is to everybody.
Short answer, yes.
Long but still short answer. The tense on that question is wrong. It's not a will be, there has been. Mm-hmm. And it will continue and it will escalate.
But I think what this last year of us all working from home has shown us is that actually humanity is quite resilient to making changes when we have to. It's just a matter of us realizing that we can and having the imperative to do so.
So this is a huge problem. We know it's a huge problem. We can describe the problem. We can quantify it in many ways. So why hasn't there been more concerted action to solve the problem?
So one of the things is something that Tomas was pointing out. The solution or the end point is very far off. The end point is always beyond, our immediate horizon, our immediate financial horizon, our immediate, lifestyle horizon as well. So that makes it really challenging to incentivize action. But I think some of the things that I was trying to point out, and we do in the School of Physics is doing brilliant work at the moment with sustainability, making very small changes every single day. And I think that's where everybody needs to start, because that lowers the energy threshold for doing the next good thing, the next best thing that we can do, and the next one. So I think we all need to just be making those small changes and every day getting better and better at doing that, because everything's so far off in the horizon on action and how things come about.
I think culturally we are not good in the present moment through the economy and through politics at dealing with long-term change. And so that's one of the really promising, hopeful things about what I talked about in my presentation, is that because wind and solar in particular, but also battery technology, are really cheap now, you don't have to approach it as a moral question anymore, where it's something we have to force people to do something that perhaps isn't the easiest route. It is now easier and cheaper to do that than keep the status quo. And I think a lot of this comes down to the tragedy of the commons. So this idea that everybody has an invested interest in saving the planet, right? But it's really difficult as an individual to make an action that's going to make a measurable difference. And so a lot of politics is very good at avoiding those questions and doing things where they can measure an impact. And I think it's something we all have to be involved in the discussion to move the system forward.
I do have a slightly political answer as well. I try and avoid these where possible, but because we've got a number of people on that list who are going to be graduating this year. So when you go into your career, join the union early, and then through collective action, insist that your pension provider divest from fossil fuels, because pension funds are large, long-scale investment funds, and if they're divesting from fossil fuels, then it becomes more economically viable to use renewables. And unions are good anyway.
Yeah.
Tom, I think we've time for maybe one or two questions before we finish up. Do we have any questions?
It's fine. I was just going to reiterate.
No, Tom. I was going to ask you a different question, because I think your talk very nicely illustrated how difficult it is to really quantify CO2 and see how it's cycled through different systems. So do you think that's contributing to our models? That kind of variability in how we measure it?
Yeah. Everyone wants a more certain model, a model that you can run an experiment with and have a real idea of what it's going to play out. And for some questions, we are there. The overall general trend is absolutely, but being able to get to the point where we can go, right, okay, this area here, not going to be able to grow anything there anymore. This area here is going to flood. Those kind of detailed questions, the ones that people really want to know individually, are much, much harder, and basically require better models. And part of making those models better is more powerful computing and things, but we're probably there with a lot of that, is being able to figure out, okay, is this little term in here, should that be a 7 or should that be an 8? But
okay, thank you very much, Tom. Okay, so I think we've had a few different kind of aspects of climate change covered. One that's coming up quite consistently is nuclear power, and both why are people afraid of it, and how much of a role is it going to play in the future?
Yeah, so I mean, for someone that started out doing a lot of solar and wind, I kind of deliberately made a decision to go back to the lab to do research in other fields, because wind and solar, the questions from a physics perspective are kind of answered, and they're things that we're rolling out. Whereas, we have about 10% of the global electricity demand comes from nuclear, and it is a clean technology. And the trouble is, if we only have wind and solar, the grid balancing becomes really challenging. And energy storage can definitely help with that. But having some aspect of baseload power production from nuclear makes the question a lot easier, because if you imagine Hinkley Point C, which is currently being built here, just sort of an hour south of here, that's 3,200 megawatts of electricity. And when you consider how much power it's going to be producing, how often, that's on the order of about let me just get the maths right. It's about 3,000 wind turbines. So it's 3,000 wind turbines is going to take up a huge amount of land or sea, which we don't have a great deal of resources of. So I think it's important that we consider it as not get into a competition between them, because I think we don't have time to afford to find the one technology which will save us. We have to use a bit of everything.
I think just to weigh on that, because there's a few sort of similar questions and similar comments which were around kind of so the carbon impact of building the renewables and building nuclear fuel extraction. Those are factored into these calculations. Like that's part of, yeah, we know, we thought of that, and yeah, it still comes out as being obviously better. There was a similar question around sort of the ecological impact of offshore renewables and stuff. And the thing you have to compare it to, you're not comparing it to not building a wind farm, you're comparing it to letting climate change continue. And it's very, very easy to calculate that.
Yeah, and in general, most of these technologies will pay back their embedded carbon cost within the first 6 months. And so they're producing a positive effect on the climate for the rest of their life. So I think, and the other thing is that everything has an embedded carbon cost, right? Whether it's a nuclear power station, a solar panel, a car, they all require energy to produce, right? And so that kind of argument, it's important that we consider all of the possibilities, not just, renewables have that embedded cost, but everything else does too.
Okay, I think we'll probably bring the session to a close there. I just want to say thank you very much to everybody who joined us today. Thank you to our panelists, Dr. Hannah Wakeford, Dr. Tomas Martin, Dr. Jon Fellows, and Dr. Tom Hull. Your contributions were fantastic. Thank you very much. And we hope that this is the beginning of a conversation around physics and climate change. Thank you very much.